We're going to continue Chapter 6 with Section 6.2 on the definite integral and net change of a function. So, unlike an indefinite integral, a definite integral says that I want to continue to integrate this function, but then at the end I want to evaluate it at two endpoints, b and a. So in this case, what we would do is we would still integrate our function as normal, and then we would plug in f of b minus f of a once we finish. And we can abbreviate this process with this symbol with a line. Remember, we used it earlier when we were trying to find the value of a function at a specific value of x, that is. And now we can do it for two different values. So let's have a look at a couple examples to really solidify what this means. So for our first example, we're going to integrate the function 2x from 1 to 3, meaning from x equals 1 to x equals 3. So we would still find the antiderivative of 2x, which is x squared plus c. So using the formula, that would mean that we would find f of b minus f of a, where f of x now is x squared plus c. And now we're going to find f of 3 minus f of 1, which would be 3 squared minus 1 squared, which is 9 minus 1, or 8. So I feel like definite integrals are much easier to understand when we have a concrete example like this. So let's try another example, this time in the form of an exponential. So here we have the definite integral from t equals -1 to t equals 1 of e to the negative t dt. So we know our function of t is going to be 1 over k, which in this case is -1, e to the kt, which is -1t. And we're going to evaluate it from t equals -1 to t equals 1. So what we're really looking at then is negative e to the negative t from t equals -1 to 1, or f of 1 minus f of -1. So f of 1 would be negative e to the -1 minus negative e to the -1. So once we start looking at a bunch of these negatives, we end up with a positive e to the 1. So we end up with negative e to the -1 plus e. So this ends up being, I would leave it here if you want an exact answer, and the decimal equivalent is about 2.35. Just like we had rules for derivatives and for indefinite integrals, we also have some rules and properties for definite integrals. You'll recognize the first one as our sum rule. That one hasn't changed. The second one is also the sum rule. It just has a difference instead of a sum. The third one is our constant multiple rule, which we have seen plenty of times at this point. What is new is number 5. This one is really interesting because if you look at it, the definite integral from a to b of f of x is the same as the negative integral from b to a. So if we go from a to b, it's positive. But if we go from b to a, we can switch it around to a negative. Interesting, huh? And the other new one that's kind of interesting is if you want to take the definite integral from one value to itself, your net change is 0. There's no getting around that it's 0. You start in that place, you end in that place, you didn't go anywhere. So your net change there is 0. And this last one is kind of cool. It says if you want to take the integral from a to c and add to it c to b, it gives you a to b. The other way to think of that one is the integral from a to b of f of x dx plus the integral from b to c of f of x dx is equal to the integral from a to c of f of x dx. That's the more common application of this last rule. And we're going to be using some of these in our following examples. The first example I want to look at with some of these rules is we have a definite integral from 1 to 3 of 6x minus 18x cubed. Then we subtract from that 2 times the integral also from 1 to 3 of x minus x cubed. This is where we can put some of those other rules into practice, but we're going to do it a little bit in a backwards way, because we can say that that's really the integral from 1 to 3 of 6x minus 18x cubed minus 2 times x minus x cubed, because these are going, both of these definite integrals are going from 1 to 3. So we can combine them together. So this is sort of the reverse of the sum or addition rule. So what ends up happening then is we can make this the integral from 1 to 3 of 6x minus 18x cubed minus 2x plus 2x cubed. And if we put a few of those things together, we end up with, let's see here, we could do 6x minus 2x and negative 18x cubed plus 2x cubed. We end up with negative 16x cubed plus 4x dx. And now when we want to find that integral, we know if that's negative 16x cubed, that's negative 16 times, well, x cubed would have come from 1/4, x to the 4th, and then plus the 4x would be 4 times, well, that means that's x to the 1, so that came from an x squared, so it's a 1/2 x squared. And this whole thing is being evaluated from x equals 1 to x equals 3. So we end up with, let's see here, negative 4 x to the 4th plus 2x squared evaluated from 1 to 3. So we end up finding then that we get negative 4 times 3 to the 4th plus 2 times 3 squared minus negative 4 times 1 to the 4th plus 2 times 1 squared, or a negative 324 plus 18, and let's see, that would be minus a negative 4 plus 2. So we end up with a negative 304. For example 4, it says if we know that the integral from 0 to 6 of f of x is 8, and the integral from 5 to 6 of f of x is 7, then we need to know what the integral of 0 to 5 is. So this is where we employ that last rule on our page, where we can say, I want to go from 0 to 5, and then I want to go from 5 to 6, and if I do that, that's the same as going from 0 to 6, because I'm looking at the same function everywhere. So what I do know there is I know that the integral from 5 to 6 is 7. So what I don't know is the integral from 0 to 5 of f of x dx. But I do know from 5 to 6 it's 7, and from 0 to 6 it is 8. So I know that the integral from 0 to 5 of f of x dx then has to be a number that adds to 7 that will give me 8, which is 1. So it looks complicated, but this is actually one of the simpler problems we have. Just put the A's and B's in order, so 0 to 5 and 5 to 6, add those up to get you 0 to 6. Put them in numerical order, and you should find these types of problems really straightforward, hopefully. How about the integral of 4t plus 3/2 from 0 to 2? Well, we can make this the integral from 0 to 2 of 4t dt plus the integral from 0 to 2 of 3/2 dt. Well, that makes this 4 times integral from 0 to 2 of t dt plus the integral from 0 to 2 of 3/2 dt. Well, we know this one would be 4 times, and we know that's t to the 1, so it would be 1 over 2 t to the 2, and that's evaluated from t equals 0 to 2, plus the integral of 3/2 dt, which, remember, if it's just a number, means it came from a t. So 3/2 t from t equals 0 to 2. So when we evaluate each one of these, we find out, well, let's see here, we get 2t squared from 0 to 2 plus 3/2 t from 0 to 2. So that would be 2 times 2 squared minus 2 times 0 squared. The second term would be 3/2 times 2 minus 3/2 times 0. Well, once we eliminate the zeros, what we really have is 8 plus 3, which is 11. Let's try another one. We can break this integral, that is from -1 to 0, of 3e to the 3t plus t dt. We can break it up into, let's see here, 3 times the integral from -1 to 0 of e to the 3t dt plus the integral from -1 to 0 of t dt, which means we get 3 times 1 over k e to the kt, so 1 over 3 e to the 3t from -1 to 0, plus, well, that's t to the 1, so that came from a 1/2 t squared from -1 to 0. So let's plug those in. After simplifying, we end up here with e to the 3t from -1 to 0 plus 1/2 t squared from -1 to 0. So we end up with e to the 0 minus e to the -3 plus 1/2 times 0 minus 1/2 times -1 squared. E to the 0 times 3 is e to the 0, which is 1, minus e to the -3, while 1/2 times 0 squared is just 0. -1 squared is 1, and 1 times -1/2 is still a -1/2. So if we put the 1 minus the 1/2, we get 1/2 minus e to the -3. And as a decimal, it's about 0.45. For example 7, we're going to compute the integral of e to the x plus e to the -x all over 2 from 0 to natural log of 2. The easiest way here is to pull this 2 that's in the bottom out. And remember, that is 0 to the natural log of 2. This is 1/2 times e to the x plus e to the negative x dx. So we can bring this 1/2 to the outside of our integral. So we have 1/2 the integral from 0 to the natural log of 2 of e to the x plus e to the negative x dx. Well, the integral of e to the x is e to the x, and the integral of e to the negative x is 1 over -1 e to the negative x. And we want to evaluate it from 0 to the natural log of 2. We do a little simplifying, we get e to the x minus e to the negative x from 0 to the natural log of 2. When we plug those values in, we get 1/2. Well, let's plug in natural log of 2. E to the natural log of 2. Yeah, I think that sounds a little weird, but it's okay. You'll see why in a moment why we wanted these natural logs. And e to the negative natural log of 2. Minus 1/2 times e to the 0 minus e to the negative 0 is still 0. So what happens here is we have 1/2, but e to the natural log cancels out and we're left with 2, minus, well, this takes a little explaining because this negative goes up and becomes a power to the 2. Remember our powers of log, so we get e to the natural log of 2 to the negative 1. And from there, we're subtracting 1/2 times, well, e to the 0 is 1, minus e to the 0 is also 1. So that term is just going to become 0, because 1 minus 1 is 0. Well, e to the natural log cancels out, and now I've got 1/2 times 2 minus 2 to the minus 1. Well, 2 to the minus 1 is 1/2. So what ends up happening is I have 1/2 times 3/2, or 3 over 4. Yes, you can plug all of this into your calculator if you want to, but the more work you show me, the more partial credit I can give you. If you would like some more examples to work through for this section, please look up your ebook on Pearson or look through the other materials available in the distance learning module for section 6.2. And don't forget to do your online homework for section 6.2.